I'm seeing a lot of the same names and faces as when I've joined these calls in the past. Yeah, I'm lucky I have the fiber optic cable option now, so I'm way faster with my own Wi-Fi.
Yeah, you're looking sharp today.
Yeah, you didn't maybe didn't know that, Alec. Last week looked like you were in the middle of a steamy shower or something.
Oh yeah, I was. I was sitting outside. It was really hot. There were like a bunch of flies swarming around my head. Yeah, I still haven't shaved, so I don't know if that's helping. But yeah, I wonder what like weird sort of bad habits I've developed during this pandemic that are going to remain true when I get back into interpersonal, conversations and interactions generally. Hopefully,
yeah, right. Look at the call. Nobody's wearing pants or shoes.
Yeah, yeah. Yeah, that was a tough go last time. I got a lot of mosquito bites during that. I hear you there about t-shirts. Yeah, the oil industry is like at some kind of medium. It seems like I was surprised that often in Silicon Valley I did have to dress up. I was kind of like expecting like, yay, it's t-shirts forever from now on, and then like, no, you got to wear it depending on where you're going and what, I don't know, venture capital firm you're walking into or something. And oil and gas was just like, at Shell, we had the rule you have to have at least one button on your shirt. And so like that's sort of formal, I guess. But maybe that's changing now.
The big guys tend to be more coat and tie types, but certainly an awful lot of the companies are jeans and boots is pretty formal.
Yeah. Yeah, I feel sorry for people who like dressing up.
It's a good skill.
Yeah, my dad is really good at that. I think I've let him down.
It gets to the dress for the job you want, not the one you have. And there's definitely something to be said for that.
Yeah, that's a good.
We'll start in just a few minutes. Let people keep joining, and we'll start in maybe 2 minutes or so. All right, everyone. Well, thanks for joining today. I'm sure there'll be some more people hopping on as we go, but we'll get started. Thanks everyone for joining. I think many of you know each other. Hopefully someday we'll get back to having some in-person events, but for the moment we're kind of trying to continue the webinar series and helping us all learn a little bit more about tools that we can bring back to our offices and our work and try and be a little better about what we're doing and know more of some ways to apply code and digital tools to our workflows. Today we're retrying with Alec Walker talking about random forest. And then next week we're still on with, I believe Michael Hardy is going to talk about Streamlit, which is he uses for building interactive web apps. And that's, I think, on the 27th, and we'll have another email that goes out and a LinkedIn post for that event. As ever, if you'd like to be included on emails, the distribution for things, please contact Mindy, Stone, or myself, and we'll get you added. Excited to have everyone here. Please take a look at some of the people on the call and try and get to know each other a little bit. I think there's a lot of really smart people who are doing really cool work at different parts of the industry. And one of the really sort of valuable things that we're trying to do with this group is help us all kind of go up some of the learning curves of using these digital tools together and trying to meet people that are at other companies that are doing the same things. And we've all kind of learned some tips and tricks that we're using. So reaching out to some of these people on the call and getting the conversation going between ourselves, kind of using that networking opportunity has been super valuable for some of us and something we want to build on going forward. So with that, let's go, Alec.
Cool, thank you. Yeah, it's really cool to be on here. I've joined a few times in the past and been like really impressed with everybody. So I've spent some time messing around with random forest and some of these other machine learning methods, and I'm expecting that I'll get a lot of great questions, and probably people will have other ideas and maybe things to show that are equally useful or more useful. My own experience with this is like, if I'm trying to drive decisions using data, like that's kind of like what you guys are all about, and I'm working for a company and I use a data science method that is something more than putting a best fit curve on Excel or using solver in Excel. Even if I arrive at something that I'm really convinced is awesome and I want to share it and use it to make some kind of decision that's bigger than just me, I have wound up in the past in a position where I have to like get some buy-in. People don't necessarily like understand what it's about or where it's coming from, and if I can visualize it for them, and if I understand it very intuitively myself, then I can talk through it with them and then get people on the same page better. That's kind of like where this concept came from, that it'd be worth it to try to build a tool that is useful perhaps in actually accomplishing the data science, but that is also simultaneously a tool that can be used to explain like what is going on with this data science method, and get some buy-in, and then maybe the tool is used not just by me but by others in the firm, and that sort of thing. Also, I've had a lot of experience working in Excel, because the industry, well, I don't know if it's the same for people in this group, but my sense of the energy industry, and this is backed by stats you can look up online, is like 90+% of our data is stored in Excel still. And Excel is pretty cool, and there's a lot of great stuff you can do there. It's not necessarily optimized for handling large data sets and doing machine learning, but that doesn't mean that you can't create tools in Excel. And so I'm used to having to work in Excel with clients, at least for part of what I'm trying to do for them or with them or whatever. So I have, if you're wondering like, why is all this stuff in Excel? Like, we can sort of start there, but of course this is data science, and you can use whatever you want to implement it. And if everyone wants to switch to Python, that's totally fine. But for the sake of trying to explain this method, I thought Excel might be a good way to get going here. So I'm going to share my screen, and looks like this is working. Oops. Yeah, so I might need you guys to help me if I should fast forward through this, but often when it's like, hey, somebody wants to learn about a machine learning method, but we dive into the method and there isn't a context of like, what is machine learning, then it's good to kind of start there. So I'll kind of go through this quickly, but feel free to make me go faster or slower, just depend. Like if everybody is totally up to speed on this, then we can skip through it pretty fast. But it's important to kind of know, like, there are a lot of nebulous terms in the world of data science, and machine learning is one that I don't think should be nebulous. That like has a nice kind of strict definition, And if we're talking about machine learning, we should be talking about machine learning, not about something else. So Venn and Forest is a machine learning method. So the concept of machine learning is we have some kind of model, and that model is overlying like data, and the model is meant to describe that data so that either we can make some sort of prediction or we can make some sort of classification. But just think about having a model, whether it's like a line on top of some dots or something else. Machine learning is the process of using that model to make a guess about what's happening with your data, and then checking the accuracy of that guess against the data, and then revising the model based on the accuracy. And then, at this point, you have a revised model, so you don't need the original. And you continue on in this way. The machine continues on in this way, making guesses, checking accuracy, and revising the model until at some point when it checks accuracy, it's better than whatever the threshold, the tolerance was that you set as the human. So we can exit this loop and, hey, now our model is a better model. And because we started with the model and we got to a better model and the machine kind of did the iterations that got us there, we call it machine learning. So just a minute ago, we've got, best fit a curve on Excel, and, there's Solver and, various tools like this have been around for a really long time. Machine learning isn't necessarily new, and there's like a lot of hype right now about like amazing things that are happening in AI, and robots are going to be walking around and talking and thinking and rivaling the capacity of the human brain. I think a lot of that is overhyped, but impact that machine learning and that what we call artificial intelligence that's practical and related to machine learning to drive decisions using data, that is not overhyped. Like that is already changing all kinds of amazing things like very quickly. So it's good to be focused in on that. Quick example of machine learning, and say this is a oil well. So we're producing some hydrocarbons from this, and we've kept track of that decline curve over time. And maybe we want to use machine learning to make a prediction about what kind of production we'll get next month. So if we were to go in this loop here, maybe we start off with our first guess, and we have some guess that looks something like this. This would not be a very good guess to predict that next month. Just as a human, we can look and see here that this doesn't seem to fit very well. The machine would have to make some sort of guess, like by checking whether the model is fitting or not fitting, and checking the accuracy that way, measuring the distance between our model and the actual data in each case. And it could continue on this way until at some point it checks the accuracy and, hey, it's seems to fit our data pretty well. This is pretty simplistic, but just like you can get the sense there's probably a lot of ways to apply this in the workplace. And because the machine got us there, we accomplished machine learning. And then we can actually use our model to do something useful, which is not an unimportant part of this. You don't want to just build models over data. Like there should be some goal, and that goal should have been why you started it first. So there's two important categories of machine learning here. There's regression and there's classification. Regression is, we're fitting some kind of model here. Again, it's a straight line to some points, and this is the real data. And maybe the question is, where's the next dot going to be? Should it be out here? If this line describes this data, then maybe this is time series data, and we want to see where's the next dot going to be. But it's not always like that. So it's not just prediction. Sometimes it's like, we don't have this dot, this input, but what would the output be if we did? Let's try something that we haven't done before. These are the things we have done before. What result should we expect if we were to try this? Or maybe the result would be something like this. That's still regression. Regression is also like, what's the lowest dot? Maybe there's something interesting inside of this this model that we've created that matters especially to us, and we're searching for something that's already there. This is all regression. Classification is kind of less common, I think, in how people are already using things that are in approach machine learning. So it's worthwhile just discussing briefly here, just to make sure that the distinction is nice and clear. So say you've got some data points, and you want to see whether if you add a new data point, it belongs to one category or another. So like a quick and silly example is maybe you have two nieces, and your nieces, one of them loves tanks and the other one loves puppies. And you've got a bunch of pictures of tanks and a bunch of pictures of puppies, and also a bunch of pictures that could either be tanks or puppies. And you've got so many in that third category, it's going to be a pain in the butt for you to go through that folder and look at every picture and say, oh, this is a puppy, send it to niece number 2. Oh, this one's a tank, send it to niece number 1, something like that. So what you might do, and this is a classification example, is create some algorithm that will analyze the pictures that you know are tanks from your very first category. And it would do things like compare pixels, across the picture and look for patterns that emerge. Like maybe there's this long thing that sticks out here, and there's darker colors on the bottom or something. And then similarly, evaluate the pictures that you know to be puppies and look for things that stand out, that emerge naturally from those pictures. Like maybe there's these 3 dots that are sort of a triangle typically, and there's something else that sticks out, but the color is a little different and the bottom's different, something like that. So then when you feed it a new picture, it can say, well, this new picture is more like this category. It fits in here more than it fits in over here. This is what happens generally when we use like Google search for an image. Say we're looking for more pictures of puppies because niece number 2 wasn't, as totally overjoyed as she could have been, and there's more pictures of puppies than anyone knows what to do with. So if we search for cute puppy on Google, it'll figure out, is this a picture of a cute puppy or just not? Is it something else generally, a tank or anything else? And only if it falls inside of a certain proximity to what the model has sensed constitutes a puppy, as opposed to an older dog or a young wolf or something else that's kind of similar, then it won't include it at all in the search results. The closer to the center it is, the higher up in the search results. So that's classification versus regression. Super quick. So one more recap. We've got a model, we make a guess, we check the accuracy, revise the model. The computer does this part. It's up to us as people to figure out what is the model that we're going to use. How are we going to decide when it's better enough that we can exit this whole thing? How is that going to be determined? And then in addition, how are we going to revise the model? So if you have all of these parts, you're dealing with machine learning. Okay, so now we can talk about random forest. Should I pause for a minute, or should I just keep blowing through this? Typically, would you think it'd be, should I wait for a few questions, or
I think carry on as you like. Okay. If anyone wants to ask a question right now, that was a really cool starting point for just the framing and kind of the basics of an inversion.
Cool. Okay, nice. All right, I'll do that. I'm used to Zoom, so if somebody does have a question and they type it, I might not notice it right away, so just interrupt me if I get to some breaking point.
I'll watch, and if people type, I'll keep track.
Okay, thanks. All right, so random forest. So I think the best way to learn about random forest is to build up an intuition using like some kind of example. And then what I'll wind up doing is I'll introduce 3 concepts one at a time that seem like they're really independent and kind of non sequitur. So just bear with me and it'll be kind of strange. And then I'll tie them together at the end. And I think it's a really cool and elegant like thing that emerges, which is, random forest. But you have to kind of suspend your disbelief for a little bit when I'm on the way there. So let's say that we're all a company and we own these oil assets here, and we're trying to decide whether we should sell them right now or wait. And there's a lot of wacky stuff going on with the price of oil, and maybe that's affecting the price of our assets, and maybe someone's offering to buy them and maybe not. So let's say we've already done all of our market analysis on that. And somebody asked an interesting question, which is, I wonder if, like, independently of everything else, if we normalized all of our data outside of this one question, is the field in question, one of these fields, is it worth less if we've owned it for a longer period of time, independently of whether we've actually like extracted anything from it? Just the fact that it's been known and owned, known about and owned for a longer period of time, is that gonna like make it worth more or less? And, typically the response to a kind of academic question like that would be like, well, just look at the total oil extracted versus the proven reserves, and like, let's figure out what this is really worth. But maybe the market isn't rational, and maybe there's some correlation that we could discover that would be interesting. That the correlation between the age of the asset operation and the price of that asset. So how long has it been operated for, and what is its value? So just for fun, let's pretend that that's our job, and we're going to check that out. So these are our assets. Should we sell them or wait? What's the simplest way to check the dependency on age? So I'll pull up a file here, and this will get us, I'll share this file in just a minute, but I want to talk through, let's treat these as like more slides here. So here's these are each one of these is a sample. So each one of these is an asset. It's some kind of oil field, and all we've got here somehow normalized in a nice way. All that we have here is the number of years that it's been operated and the value. And the value is like, ranges, looks like from 2 to 9. So that's it. Like this is the only data that we have. So if we wanted to figure out, does the number of years of operator control affect the price? We could just plot these two things against each other, right? And then if we were to do that, like, we would get some kind of line that could describe that data, and we could see how it fits. So let me start here. So it looks like there's some kind of descending relationship, which might make sense. If it's been owned for longer, typically it's worth less, assumed to be worth less regardless of everything else. So that might be the way that we would approach that problem. But just for the sake of argument, and here's our first kind of strange non sequitur. What if we ignored all of the years and pretended that we didn't even have this data? And we just wanted to like predict that all the assets that we might ever encounter have the exact same value. How would we do that? Like, what's a good way? It sounds like a dumb idea, but let's just pretend, like, what's the simplest, dumbest model that we could ever come up with, where no matter what the input was, however many years the asset has been owned and operated, we always predicted the exact same value. How would we come up with a value that's like somewhat reasonable? And typically we would here's somebody unmute, so go ahead and answer that if you have an idea. How would you come up with a single number to predict the value of any asset?
Just the average?
Yeah, you could just take the average, right? That's probably the easiest and dumbest way. So if I just took the average here and treated this like it's its own model, then no matter what I put in here, anything that I haven't seen before, I would just predict this value for all of these things. Just like super dumb, but that's one way. We could also maybe do the median or something, or the mode. The median mode, this is like middle school stuff. Let's call this our simplest, most naive model for how we could make some sort of prediction for the value. Everything is going to be 5.8, 5.77. Okay. So there we go. That's our mean. Perhaps the most obvious. So now what I've done is I've taken this and I've treated it like it's a real model here. And here is our model. It's just like this straight line. So no matter what this input variable is, our output is always just predicting this straight line, right? We're almost there. Versus what we first thought might be a good idea is just to plot this thing, right? And if we plot this line looks like it fits this blue data, which is the real data, much better than this dumb average prediction does, right? And the way to prove that, and now we're entering our second non sequitur here, it seems to be, is this R squared value, right? So as a human, if I just look at this dotted blue line, which is the best fit line that I attached from Excel to my plotted blue data, which is my real data, this linear model has an R squared value of 0.51. So this is how a computer would come up with the accuracy. This is R squared value is a measure of how our model describes the variance in our actual data. And so this is how the computer would make a distinction between the accuracy of this model here versus this just predicting the mean, really dumb model. Okay, so, but what is R squared? Like, what is R squared all about? And that's the next thing to talk about. So R squared is like something that we're probably all used to. And typically the concept is it ranges from 0 to 1. If it's 1, then it's a perfect fit. We've described 100% of the variance in our data. If it's 0, then we're not doing very well. It actually can get below 0. But let's talk about like, what is it mathematically? What is it actually doing? So it is the coefficient of determination, okay? It tells us what percent of the variability in our data is explained by the model that we have to describe our data. So we have these two components to it. So R squared is 1 minus this SS underscore residual over SS underscore total. What are those things? Sums of squares. So sum of squares total is, and this is how we calculate it, it's each price. So each actual price here, each actual value, minus the average of all the prices squared. So we take the difference and we square it. This is almost like what we're doing to measure the distance between points in two-dimensional space. So we're taking the difference between this average here, which is a single guess for every single point. And for each one of those points, we're measuring the distance, the difference between these two things, and squaring it for the value, right? So that's this SS total sum. The SS residual is we're taking each price and we're subtracting our predicted price rather than the average, and we're squaring that. So the predicted price is this line. So what's the difference between taking the space between our average here and the actual blue line versus this line that actually describes our data and the data? So blue dot versus orange line on the one hand, and dotted blue line versus actual data on the other. And we're taking 1 minus that quotient. So what this means is how different is each real price from the average? How different is each real price from each prediction? And we're comparing those two things. We're taking 1 and subtracting it by that fraction. So basically what we're doing with an R squared is we're comparing the accuracy of two separate models. The first model is what happens if we just predict the average for everything. And the second model is, well, what happens if we actually like plot the relationship here? Our actual model in question. And that model in question is whatever we got the R squared value for. So it doesn't have to be linear regression here. It could be something more complicated. But the thing that's like really gave random forest, like really got it going, was this insight here that really all that R squared is, a great way to think about what R squared is just the comparison of two models. Whatever model you have that you care about, that you built and are trying to put effort into, and this other model that's just really dumb, that just predicts the average for everything. So if you think about R squared that way, you've got 1 minus how different is each real price from each prediction over how different is each real price from the average. 1 minus that. Our model is like, we're checking out how is our model doing versus the model where we just predict the mean. Okay, so then the insight here is what would happen. Well, here I do the calculation, so I'll talk about that first. So R squared of 1 minus our model over predicting. So the best fit line that we got, this was the R squared was 0.51. And what would happen if instead of this model here, this y minus 0.55x plus whatever, what would happen if instead of that, we just treated our actual model as predicting the mean. Then we would have whatever error from our model, which is predicting the mean, divided by predicting the mean, which is 1. So we'd have 1 minus 1, which is 0. So r squared goes to 0 if your model just predicts the mean. So it's kind of defined to have a baseline here of predicting the mean is like the simplest, most naive model that you can have. Whatever our dependent variable is that we care about, if we predict the mean, we get 0, and that's where we start. And anything better than 0 is we're starting to describe more of the variance. So that's how r squared works. And how would it get below that? Well, we could predict something that's worse than the mean. We predicted something, say, that's super, super far away from each one of these points, further away than the mean. Well, then we would have a larger value here than predicting the mean. So we would have a fraction that is bigger than 1. We would subtract that from 1, so we would get a negative number. So you can have a negative r squared if you have a really, really bad model. But put in the effort in, and you can probably do better than predicting the mean. All right, so here's the random forest inspiration. Now I can finally tie all these things together. Instead of doing linear regression, what if we instead made a single decision tree and predicted one or the other of 2 different means? So rather than predicting one mean like this, where we predict the mean of all of our values, what if instead we decided to make a prediction for just some of the values? So maybe these ones, and predicted the mean for them, versus these ones here and predicted the mean for them. So here's what that could look like. For example, we want to predict the value of a new asset that's based on how long it's been controlled, like what we've been saying. If the asset has been controlled for longer than 4 years, and we've got the years here, then predict the average of all of our samples that have been likewise controlled for longer than 4 years. So we predict the mean. Let's say we had a new sample come in and it was 1.5 years. So that's not longer than 4 years. So what we would do with that is, for anything that's controlled up to 4 years, predict the average value, not years, but value, right? This is our dependent variable, of all of our samples that have been likewise controlled for just up to 4 years. What does that look like? So this is what that looks like. So I've just sorted these by years. So here's stuff that's been owned up to 4, including 4 years. And we predict the mean of just these things, and we get 7. And versus anything that's been owned for longer than 4 years. And we predict the means of those things, and it's 4.8 for those. So then what we could do is we could pass in, if we had, say, a new asset and it had been owned for 1.5 years, and we want to know, like, what the heck is its value? Well, what we would do is we would say the value is 7. That would be our prediction. Why? Because it's been owned for less than or equal to 4 years. So we send it up into this split in our decision tree, and we predict just the mean for that. So the way that we do this is in random forest, if we want to figure out what's the r squared value overall of this whole thing, we want to calculate the r squared value for each of these 2 things. And would we then just take the average r squared value of each of these 2 things? Like what's the r squared value if we just do the math to fit this prediction versus this value? And then what's the r squared value if we were to do this prediction for these values? And we can compare that to our overall mean. So what we would do is we would calculate 2 r squared values. One is for branch number 1, which is up here. And I try to color code this to make it simple what's happening with the math. But we take the actual value. So this is the true value. This is what our actual data is telling us. So this is the right answer. And we subtract from it our branch 1 mean, which is our new model. So our new model is this decision tree. So we're only subtracting this value for this r squared up here. So comparing how well does our model predicting compared to the actual data, that's the machine learning part, and square that. And then we divide that, just like we learned in the r squared, by our actual value minus the overall mean here. And we do that for each one of these samples. And so that calculates our r squared value for the upper branch. Then for the lower branch, we do the same thing. And so we have the actual value minus the branch 2 mean, which is this one, 4.8. So the actual value of this minus this, square that, and then divide it by the actual value this minus this, and square that. That's the branch 2 one. So if I do all that math, I get this is our actual r squared value overall. But how did I get that? Like I had two r squared values. How do I turn them into one? I don't just take the average. I have to take a weighted average. In this case, I had 1, 2, 3, 4, 5 samples down here, but only 1, 2, 3, 4 samples up here. So it's not really fair for me to say that the weighted, that the average r squared value, the measure of this whole tree, is just the average of the two branches. Instead, what I have to do is I have to weigh the average of each branch by how many samples it has in it. So I would multiply my r squared value for the second branch by 5, and I'd multiply this one by 4. I would add those together and then divide the whole thing by 9. So that's what I'm doing here, and you can follow the math. So I'll share this with you. This is the random forest intuition like explainer file. So hopefully if you work through these tabs yourself and you get through to this exercise, you can carry out this exercise and do something similar to what I've done here. And your goal for that would be to, you can follow these tabs here where I put some comments. But let's pretend that we're in a new situation and it's no longer oil and gas. It's a wacky one that I came up with, kind of like the tanks and the dogs. So let's say that you bought a bunch of Martian kittens at wholesale prices so you can sell them into Martian families. But they're really far away. They're in Mars, so you can like see them and learn anything about them to figure out like how much should you charge these Martian families to sell them your Martian kittens. So all you know about them is that they're all 3 months old so far and they don't weigh much. So you know, how much should you feed them and how long should you wait before you sell them? What's the ideal age and weight of the cat if you want to maximize the money when you sell it to whoever's buying it from you? So you have, here's a bunch of ages. This is the only information that's been sent your way about these cats. You have the age of the cat, you have the weight of the cat, and then you have the dependent variable, which is the value that cat can be sold for. And your goal is to try to figure out using a single split, a single decision tree split, how you would send a new cat if you know, what's the ideal age and weight to maximize the value here. So you can just look and see that a cat that's age 23 and has a weight of 0, which is I guess possible for a Martian cat, is sold for a lot more than, you know, here a cat that is only 3 but weighs 22, whatever that unit is. But your goal is instead to use this random forest concept and make a single decision tree. And you could choose whatever feature you wanted to make that split. So you could decide to make the split here at this feature, or here down at this feature. So I'll share this with you guys, and then I'll show you an actual random forest tool that takes this concept of making a split and using weighted r squared value and makes a bunch of splits, and then uses this a tree and then another tree and then another tree to create a forest, and how that part works. I'll pause again just in case. How am I doing on time? Do we have another 15 or 20 minutes here? Yeah, all right, cool. Okay. Got the link. And there we go. Chat. All right, so I just sent you guys, yeah, I just sent you guys a link here. This is to this Google Drive folder. Folks can download those files and play with them. One of them I didn't open. It's just a test to see if Visual Basic, which is the scripting language that comes with Excel, if it's working for you on Excel. If it's not, I'm like happy to help you set it up. It's pretty easy, and there's like a few like quick little videos depending on whether you're using Excel for Mac or Excel for Windows to set it up. But the tool that I'm about to show you, I built in Visual Basic. The reason I did that is, like I said at the beginning of the course, it's helpful to show people what's going on inside of a model, inside of a tool that they're used to playing with. If you want them to get some buy-in from you, trust your model, and then actually put it to use. And overcoming the sort of cultural that prevent more widespread adoption of data science methods is pretty significant challenge, I think, in some industries that are more old-fashioned. That's why I did it this way, and hopefully that's useful to you. So you guys have that to play with, but rather than devoting time to treating this like a course where you would play with it in the course and then get back into the next part, I'm just going to launch into the next part in case some of this was reviewed for some of you, and that way you can play with it on your own time. All right, so let me pull up this one. Okay, so now that you have some sense of how the random forest gets started, you have the sense of, instead of just predicting the average for everything, you predict the average depending on overlap with some sort of feature in your samples. And it's one or the other of two different averages. And that's going to make your overall R-squared value better than if you just predicted the average overall for every single sample you have. So that's where we've gotten to so far. Let's turn that concept into a random forest tool that can actually be used in machine learning. So we're looking at a data set here, which is a real data set, but I've really tinkered with it because I have to obfuscate it because it would be proprietary otherwise. And I changed the names, and but the relationships they're really simplified are still kind of real. So what we're looking at are performances of wells based on their various design configurations and other things. So we have the location of the well. There's Lakeside here. There's Barnview. There's Big Slate. I made up those names as replacements to actual places. There's the depth, and I normalized that to between 1 and 10. And there's the lateral length. So we drill down and then we drill out to the side, right? And the lateral length is between 1 and 10 as well. So we can assume these are all onshore wells that are horizontal wells, not vertical, and they're oil wells, not gas wells. And then the configuration was basically everything else got normalized down into this one variable. So how many stages and how many perfs per stage and how big are the stages and all kinds of stuff like that. What tools are we using, and the sand and everything else. So we have three configurations. There's A, there's B, and there's C. So we're dealing with either configuration A, B, or C. And we have these various performance things. And what if we wanted to use all of this data that we've collected in the past? And this performance is like, this is another normalized thing. Normally we're used to seeing some kind of like EUR and a decline curve. So we have a sense of when we would get our hydrocarbons, and then a breakdown of is it oil or gas and water and how much of each. I've just taken all of that and I've combined it into like a single number, just for the sake of making this easy. So a negative number here would mean that we lost money on this well, that it costs more to produce it than it's actually given back to us. Not very unrealistic given what's happening today. And performance of, here's an 11, that's a really good well. So this well has made a lot of money for us, and this goes higher than from 1 to 10. There's a 15, there's a few wells that have done very well. And the concept is you want to figure out like, well, what if we were to do X? What if we were to like, pick something like maybe a lakeside well. We want to predict using this concept of making splits. We want to somehow turn that into something that can tell us what this is going to be, what our dependent variable is going to be, if, say, we wanted to do a really shallow well. So what would happen if we went to Lakeside and drilled a super short well that had a tiny lateral length, how would that well perform? Maybe the data that we have from the past can tell us that this would be a regression, for example, using that insight that instead of predicting the single mean, we can predict one or the other of two means. So what happens here is, I'm going to go, so I just numerified the data. So that just like takes anything that was a lakeside and gives it a 1, anything that's Barnview and gives it a 2, Big Lake gets a 3, and configurations get 1, 2, and 3. So it'll find anything that's numerical, that's a string, and turn it into something that's numerical. And what this will do is it'll actually create a, this probably goes slow because I'm on a call. But at some point it's going to say, yeah, it's going to say that it's frozen, and that's just because I turned off screen updating. But what it's going to do is it's going to grab a random sample of our data, and it's going to make a split on that random sample. Okay. So I've now added a tree. So what is a tree, and what does it look like? This is what a tree actually looks like in a random forest. You can see we've got like something that looks kind of like a trunk, and then we split that trunk in the way that I showed you. And then we take each of these branches and we continue to split these. And some people call these canopy layers. So we've gone from our trunk into the first canopy layer, then into the second canopy layer, on down to, and then these are called leaves when we get to a single sample. So these are all different wells, and we've split them up until we got to leaves. So what's happening here is, here we go. What's happening here is each one of these trees is a random sample of the data that we started with. And you saw when I said create tree that I chose 10%. So I said, okay, grab a random 10% of this data somewhere. And once you grab that random 10%, then make a split with that data at one of these features. So these are the dependent variables here for each sample. So we're not going to make a split there. This is what we actually use to measure our R-squared value. This is kind of a special column in each case. But each one of these things are input like independent variables. These are like the features that might make a difference in determining what our R-squared value is. So what happens in random forest is, for this trunk, for this sample of data, the random forest tool will go through and try to make a split here and see what happens. So if A, which is location, if this feature is 1, which is lakeside, or less, then put it into one category. Versus if it's bigger than 1, put it in the other category and try making that split, and then measure the weighted average R-squared value. And if that weighted average R-squared value is high, then we're going to like that split, and we're going to make that split and commit to that split. But we have to try every single possibility. So we try making the split here, and then we keep track of that R-squared value. Then we try making the split here, and we keep track of that R-squared value. Then we try here, and we keep track of that weighted average R-squared value. And then we try here, and then we go on to the second sample, and we try making it here. And it keeps going this way until it's tried every single possible split. Where should we split our data? And it decided here that actually the best place to split our data is sample for feature 2. Okay, this fourth sample of feature 2. What is feature 2? Oh, it's depth. So if a depth of 2 or less, then send it down here. If a depth of greater than 2, then send it up here. So you can see that all the samples that made it into this branch have a depth that is greater than 2. This is the only one that has a small depth. So this is unusual that it finds a leaf on the very first split. But maybe it did that because you notice this is a 16, and these are all smaller than that. So sometimes if there's an outlier, the outlier gets flagged and separated kind of right away. And again, it tried making the split at every single point here. And it wound up only choosing this point because this had the highest weighted average R squared value across the resulting trees. So what's the R squared value for this? Well, there's only one answer here. So it's going to be an R squared of 1. But that's weighted against the R squared value here. And it still comes out to be the highest possible R squared value. We then make the next split. And so this branch gets split into this branch and into this branch. And we continue on doing that and keep splitting up each branch into its respective children branches in the next canopy layer until we're left with nothing but single samples. And these are our leaves. So that's how a tree works. I'm just going to go through that one more time, showing the notes that I took, because it's like takes a little while. It's a little like mind warping. Like, why are we creating trees and what the heck are trees? So we've got this weighted R squared value concept. We can make a split. How do we know what split to make? Well, we make this split that will maximize our total weighted average R squared value. So if we're committing to this really dumb model where we only are going to predict one or the other of two averages across our dependent variable that we cared about here, then the right way to make that dumb model work as best as it possibly can is to at least maximize the weighted average R squared value across the two resulting branches. So we continue to do that, and we continue to make branch after branch, canopy layer after canopy layer. And in my code, the way that I should probably explain this, because I'll share this with you. This 2 down here indicates the value of the selected fork feature. So it's the second feature was selected. And then this indicates, this is the value of the feature, which is 2 in this case. The value happened to be 2. That's the number that's in it. And this is like, which feature category are we talking about? So that's the column in this case. It's the second column for this. This would be the second column when we're looking at this. This would be the second column, right? So it picked the second column, and the value was 2. And then this is just a tag. This tags the branch, so that this helps me when I was coding it, because I'm not smart enough to figure out how to tell my own code how to look at the next thing and find which branches happen to be the children of the first trunk here. So I assign this random number here, which gets passed on to here. That random number helps to identify that these branches came from this original branch. And notice that then this random number here gets passed on to its children. And then they each generate a new random number that gets passed on to their children. So that's why I have these random numbers here. And then this was the weighted average R squared value of that fork that resulted. So this was the best weighted average R squared value for this one, which happened to be sample 3, feature 4. So third sample, 1, 2, 3, fourth feature. So sample 3, feature 4 gave us the highest weighted average R squared value, which was 0.477. This one gave us a 0.53 when it split this one out from these two, from the rest of these. This one gave us a 0.477 when it split this out from this, and so on. So, all right, now we've got a tree. The way that this works overall, go back into my, let's create one more tree. So the way that this works overall is whenever we pass it a new sample and we don't know the actual value that we care about, the dependent variable here, which in this case is like the value of the predicted value of the well if we were to design it in a certain way and put it in a certain location. What random forest will do is it'll look through these trees, and for each tree, it'll take the samples that we give it. So let's say we have some question like this: how will this well perform? Whoops, that's a 4, but it shouldn't be. I guess ranges to. So this is their third location, and this is the depth and the lateral length, and this is the configuration. How would this well do? If we have a well like this, what would be its resulting value? The way that the tree works is it'll look at this sample and it'll determine where to send it along this decision tree. So sample one feature 4 is, here's sample one feature 1, 2, 3, 4 is a 1. And so this feature 4 is a 2. So this is bigger than this, which means it'll send this sample to the top up here. And so far it's going to predict the average value here. But we can keep going. We can say, okay, well, this was sample 3 feature 2. So sample 3, 1, 2, 3 feature 2 is this one. And it's a 7. So we compare this 3 here, this is the second feature, to this 7, and we see that the 3 is less than. So we're going to send it to this branch where the second feature, feature 2 here, is less than 6, 6 or less. So it goes down over here. And it continues doing that until we reach a leaf, and then it will predict that this is the value that it should assign to this sample that we fed it. And that's how the tree works. So once we've got like a prediction there, and maybe that prediction is like 10 or something, then it'll have gotten to a prediction from this other tree as well. And maybe that prediction is like 7 or something. Then it'll just take the average of all the predictions from across our trees, and it'll use that to finally determine the ultimate prediction from the random forest. So we start off with trees of random data, and we split those trees into branches, and then we split those branches into more branches. And we keep doing that until we get to leaves. And then we pass our samples through, finding which leaf they should arrive at. And then for each tree, we assign that value to that sample. And then we take the average across all of the different trees. And that's how we arrive finally at our answer here. So I've only created 2 trees. This is a really small data set, and I've like messed the data set up a lot by obfuscating it and simplifying it. But let's see how we do. We only have 2 trees. So I'm going to go in here to validation data, and I'm going to say use forest. So this is what it guessed. It guessed a performance of 7 for this sample, and this is a validation data. So I actually knew that this was the actual performance. These were more samples that I actually had the answers to. So I'm just checking to see how my model is performing. And a 7 versus 10 is like, yeah, that's not very good. A 4 versus 9, that's even worse. So it's not performing very well yet. And what would I do to change it? Well, I could add more trees. I could also try to add more data into my original data set. That would help a lot. I could also do something where each tree that I create is a different size and uses a different percentage of random data from my original collection of data. So there's a few different, like we call those hyperparameters to play around with to try to tune your model so that it's a good representation overall of your actual data. And once it's fitting pretty well here, and this is what you do typically with data science methods, but once your data is fitting pretty well to your actual values in this validation data, then you come back to your test data, which is the data that you never touched until you think you finally got something that works. And then I would paste this testing data in place of this validation data. And then I would run use forest and see how it compares there. And if it still compares well, then I think, all right, this is good. I built a model that actually describes my data pretty well. And using this regression approach can actually make predictions for wells that we haven't seen yet before, looking for correlations across all of these wells that we have seen before. That's the random forest. I'm going fast because ordinarily this like takes about a day to explain in detail. So I'm trying to whiz through it here, but I'll pause there and see if there's any questions. Thanks, Matt. Oh. Do all random forests use R squared for the loss function, or can we use other variables? I've never seen it otherwise. It's always been R squared, but I don't see why you need something that makes um, yeah, you need something that makes a clear split. So I suppose you could use something else. Um, huh. I think that what matters is, yeah, you want it to be really simple to calculate, because the downside of random forest is that it's so computationally intensive. Like every single, share my screen again, but every single sample for every single feature has to be considered as a potential split. So here we only had like 10 samples, but imagine if we have like, thousands of samples to consider, and we have more than 5 features here. We have like 20. It's going to be quite a lot to look through, and that'll really bog it down. So I think that R squared is a nice quick thing to calculate. And all you need to do is to compare, given that set of data, which of the two is better, or which one of the it's not two, but which one of your R squared values that you get from testing out these splits is better. Yeah, so I don't know that you'd have to do something more complicated. It's a cool thought though. I've never even tried to do something different. Can you touch on?
Yeah. Looks like someone was asking what advantages random forest has over other multivariate models.
Oh, yeah, that's a good question. So, oh yeah, scrolling up, I see I missed that. So, random forest tends to do very well when it's less obvious to the data scientist what could be an artifact and what could be an actual correlation. So, you put a bunch of trees in, each tree is going to have like a lot of bias. Each tree is going to come up with something that isn't necessarily a good guess, because it's just a subset of data, and whatever kind of correlations emerge from this process of creating all the splits and getting down to the decisions, that process is flawed. And so you'll wind up with like something that locally is an artifact being weighted heavily in the actual determination. But when you have multiple trees and they average each other, then really the only things that survive are the true correlations that actually exist across your whole data set. So it's kind of a fascinating, like I first got exposure to this reading some papers, and I found it like really hard to understand what was going on. But one thing that like made me really interested and struck me right away is it seemed like, so we're taking a bunch of like really poor, crappy models and we're averaging them together and we're getting good results. Like, how is that ever a good idea? But it is a good idea because of the thing I just tried to explain. Like, the reason why each of the crappy models is crappy is because there's some probability of some random artifact being like emerging as something that's heavily weighted. But when you average across a large data set, then it's fine. So major disadvantage is just how computationally intensive it is. I'm running this in Excel, and Excel seems to have problems with when it's doing screen updating and when it's not. If I have another application open that's doing screen sharing, so it makes it take longer to run here than when you guys download it and try playing with it yourselves. But even so, it takes a really, really long time when you have big data sets to run random forest, but that's less and less of a hindrance, just given that like we're now, I don't know, this crappy laptop has like 4 processors and has a little GPU in it too, and you can use cloud computing to have access to a lot of processors all at once. It lends itself very well to parallel processing. That's another advantage. I can tell one processor, you create this tree, and another processor, you create this tree, and they don't need to talk to each other while they're creating the trees. All they need to do is output what their predictions are at the end, and I can just store one while I'm waiting for the next one, and so on. So it lends itself very well to parallel processing, and that kind of redeems how computationally intensive it is. The advantages. Oh yeah, I talked about classification and regression. You can use random forest for classification too, which is great. The way that you do that is instead of just predicting the average across the different trees at the very end, instead you just take the mode across what the different trees had predicted. So there's a example here from the Titanic. That's like a very popular data set to play with when you're learning about some of these. I'll share that one too. Well, I don't want to take up a huge amount of time talking about it, but it's a classification data set. So you can kind of see how that would work. If you have multiple trees, you just take what's the mode across all of those trees rather than what's the average, what came up most as the suggested category, and then you assign your new sample into that category. All right, and how does it create new or different trees if the first tree split maximizes R squared? Yeah, so that's a good question. So the first split maximizes the R squared value of that one split. So in here, if I have this, I'm still showing my screen. Yeah, if I have this data and I make this split here, so anything that is 2 or less goes down here, it's greater than 2 goes up here. If I make that split, what that R squared value is just that weighted R squared value is just for that split. So we're pretending that we're done here and that our model is just like that we're going to predict either this value here, a 4, or we're going to predict 16, which is the average of everything in here, and there's only one. So of course it's going to be 16. So we're predicting 4 or 16. We're pretending that's our final model. And so what's the weighted average R squared value for this if this were going to be our final model? And that's how we arrive at this 0.53. But it's not. There's still more work to do. We can then take and continue to split whatever branches are not leaves. So we can get a separate independent R squared value when we then make a split here and compare this versus this. I'm still thinking about Michael's question about other error metrics. I've never seen that before. Can I touch on eigenvectors and important data versus overinterpreting noise? On eigenvectors, no, I can't. Maybe somebody else can on this call for figuring out important data versus overinterpreting noise. That's something random forest tends to excel at, especially if you have a lot of data, because of that concept that you kind of average out all of the error. One way that I've heard it explained is like you have a tree that's going to have some error and overinterpret some noise, and that what direction is that going to be in that overinterpretation? It's going to be random, so some random error in one direction, and then you have some random error for another tree in another direction. and some random error for a third one in another direction. And the average of a bunch of random numbers, if you have enough of them, is 0. So then you wind up with a small amount of error overall, which is kind of a cool, elegant concept. Eigenvectors. Can anyone on the call talk about that in relation to random forest? I might know that by a different name, or maybe I'm just ignorant and I don't know about that at all.
I was just asking about columns and parameters that are driving the signal as opposed to things that are variances that are in the data set that aren't actually driving the result, but might get spurious correlations.
Oh, okay. Yeah. I guess I answered that okay. I mean, I like to, if I'm showing this to somebody who's using it for like that concept that, oh, look, this 16 got moved aside quickly. Maybe that means something to you. Like if you can show how the tree is doing its thinking, sometimes people are like, oh yeah, that would make sense that perhaps the, or perhaps the, oh no, feature 2, the depth would have mattered the most in this certain area or something. If I pull up that Titanic thing, it's easier to show that. Here we go. Some cool things typically happen. Okay, so this is the same exact tool, but I put different data in it. It's not here. This is the actual training data that it's getting. So we have, this is a famous data set that some of you might have seen before. We have the passenger class, whether they're male or female, what their age was, if they had a spouse or a sibling, and on the ship with them, how many. This is from the Titanic, the boat that sank. Parents or children, and how much they paid for their fare, what port they got on when port of embarkation when the boat was going around, and then whether they survived crash or not. So this is our dependent variable. So this is a classification problem. We want to figure out whether they survived or didn't. So numbers in between 0 and 1 aren't helpful. But because there's only 2 categories, we can just round to the closest whole number here to see if our model ultimately predicted that they died. So if I create a tree, we might be able to just look at the tree and see what kinds of things emerge that matter. I made it a smaller percentage because it's the bigger data set. I think process. It's kind of fun to like turn the screen updating off. I mean, turn it back on so that it stops going into this mode, so you can watch what it's doing. For some reason, I can't get it to do that when I'm sharing my screen versus, if you were looking over my shoulder in real life, because then you can see like how it's calculating which weighted average and which sample it's doing that for. So you can have it pause if you want to and poke around and figure out what it's doing on the street. But let's explore more. I might have picked too big a sample. It might take a while. I wonder how many. I forgot to check how long a data set is, and I just said 5% go. But we'll see.
I like the way of using Excel as a tool to kind of sandbox even a complicated random forest model. That's a neat way to express it.
I think like arrays in Excel are just so funky. You can't. Maybe somebody else knows how to do this, but I can't figure out. I don't think there's a way to define an array and then without redefining it if I change its length, if I need to change its length, which makes it really, really tough. There we go, it's done. To store information temporarily inside of Visual Basic itself. But so that's the downside of Visual Basic. But the upside is that if you're storing everything in Excel, even temporarily instead, it really helps people to understand what steps there are, even if they don't understand the code behind it. So you can just like show what's happening. All right, so yeah, this isn't that good. It's only 20. So sample 2, feature 2, sample 2, 1, that's sex. So I think 1 is male and 2 is female. Gotta open the other file where I saved that information. Yeah. So it decided that right away from this tree, from the experience that's captured inside of this tree, being a girl versus being a boy had the biggest initial impact on whether you survived or didn't in a disaster. And so what you'll see here that kind of helps to show that is there's a lot of ones up here, and there's only 1 0. And then down here, we still got some more work to do to figure out what's up. So these are all women, and there was 1 woman who died here, and 7 that survived, or 6 that survived. So already we're starting to get some sense of what might be, interesting and important in our data. But the way to check this as a human would be to then create more trees and see if that still holds. And if it does, then it's less likely to be noise and more likely to be music.
Alec, this was awesome. I really enjoyed it. Does anybody else have any more questions they want to ask before we wrap up? Well, thank you so much for an awesome introduction to the random forest. It definitely helped me understand some parts of it that I didn't fully grasp before. I like the way you visualize a lot of this. So really, thank you much for presenting and for taking time to talk with all of us. As I said before, I think Michael Hardy is speaking next week on Streamlit apps. So we're getting pretty close to where everybody pretty soon is going to be building apps online for themselves to build their own random forest models in R and Python and AWS and whatnot. And I look forward to kind of seeing what kind of projects we can build, or if we can do some fun hackathon type challenges in the near future. We'll have some posts and emails out about the next talk. Thanks again, Alec, and I'll see everyone next time.
All right. Thanks,
Thanks,
Thank you
Alec.
so much, Alec.
Thank you.
Bye, everyone.
See you, Kurt.